This is going to be a super quick look at the properties of exponents. We'll dive deeper into each of these later. The first property we're going to look at is the power of products rule. That says that if we have a term a to the m power times another a to the n power, what we end up doing is we add those exponents together. So if we look at a numerical example, if we have 2 squared times 2 to the third, that's the same as 2 to the 2 plus 3, or 2 to the 5th power. You can confirm that yourself by doing 4 times 8, and you know that's 32, and that's also equal to 2 to the 5th is equal to 32. Both of those are the same. We can do this with variables, though. We can do x to the 2nd times x to the 7th, and that will be equal to x to the 9th. We can do it with two variables at once. If we have x to the 2nd, y to the 3rd, and we're multiplying that by x to the 5th, y to the negative 1. Here we can add those exponents together because multiplication is commutative. So we can do the x squared times the x to the 5th and get x to the 7th. And we can do the y to the 3rd times the y to the negative 1st and get y to the 2nd. And that would be simplified from the statement above. If you have coefficients, an example like 2x to the 3rd, y to the 2nd times 4x to the 5th, y to the 9th, then all you have to do is multiply those coefficients first. 2 times 4 is 8. Then we apply the property of exponents. X to the 3rd and x to the 5th gives us x to the 8th. Y to the 2nd and y to the 9th gives us y to the 11th. The zero power, while is actually the easiest property to probably remember, sometimes is confusing for students. A to the 0 is equal to 1. 2 to the 0 is equal to 1. 17 to the 0 is equal to 1. X to the 0 is equal to 1. Anything to the 0 power is equal to 1. Well, why is that? Well, if we look at our exponents, we look at for a pattern here. Think about 2 to the 3rd power. That's 8. 2 to the 2nd power is equal to 4. 2 to the 1st power is equal to 2. Well, what's happening here? Each time we're going down, we're dividing by 2. So if we work down again, 2 to the 0 power would be the next in the chain. If we divide by 2 again, what would we get? 1. So that's kind of a quick explanation of why anything to the 0 power is going to be 1. Now we're talking about negative exponents. So if we kind of continue our pattern from before of every time we divided the lower the exponent by 1, we're dividing by that base number there. If we went to, what would 2 to the negative 1 power be? Well, we just have to divide by 2 again, and we end up with 1/2. And if we divide by 2 again, 2 to the negative 2, we get 1/4. So the rule here for negative exponents is anything to a negative power is equal to 1 over that exponent to the positive power. So 2 to the negative 3rd is equal to 1 over 2 to the 3rd power. And 1 over 2 to the 3rd power is the same as 1 over 8. We can do this with variables as well. X to the negative 5th power would be equal to 1 over x to the 5th power, and that's all we can do. We never want to leave any negative exponents anywhere in our final answer. Now we get into the quotient power, and this is going to be a little bit of an extension of the negative power in a way. So if we have a to the m divided by a to the n, it's ultimately a to the m minus a to the n. So if we have 2 to the 5th over 2 to the 3rd, we can simplify that by doing 2 to the 5th minus the 3rd, and we get 2 squared. If you think about this, basically we had 5 2's multiplied on top over 3 2's multiplied on the bottom, and if we cancel those out, we're left with 2 2's multiplied, which is 2 squared. And of course, in this situation, we do want to simplify it as 4. If the number is exorbitantly large, we'll kind of leave it as it is. We can do this with variables as well. If we get x to the 2nd over x to the 1st, x to the 2 minus 1 is equal to x, and that's our answer. Now, we do want to consider the case of what happens when we have something like x to the 3rd over x to the 5th power. Now, this would give us x to the 3 minus 5 is x to the negative 2. We don't want to leave negative exponents, so we then would convert it to 1 over x squared. But some of you might be keen to jump right to this immediately. So I think about when we started off as x to the 3 over x to the 5, I see more x's in the denominator, so I'm going to subtract them, but I'm going to know that my final amount of x's are going to be left over in the bottom. And if I subtract 5 minus 3, I have 2 left over. I'm going to leave 1 in the numerator as my placeholder. The power of power rule says that if we have a to the m to the n, that's then the product of m and n is now the new power of a. So if we look at an example, 2 to the 3rd all to the 7th, that would be ultimately 2 to the 3 times 7, or 2 to the 21st power. That's a really large number. We're just going to go ahead and leave it as 2 to the 21st power as our final answer. Works with variables as well. X to the 2nd raised to the 5th is going to ultimately be x to the 2 times 5 is equal to x to the 10th. If we have multiple things inside of a parentheses raised to a power, they all get the exponent here. So if I have x squared y to the 5th, I'm going to distribute basically this 5 exponent to every factor inside. So that becomes x to the 2 times 5 is 10. The exponent on y was originally 1, so 1 times 5 is 5, and so that would be the simplified version of x squared y all raised to the 5th. The rational powers, we're only going to be working on rewriting them in this chapter. In the next chapter, we're going to be working on simplifying them. If we have a to the m over n, that's going to be equal to the root n of a to the m, or also we can do the root first, take the root of a raised to the m power. I always kind of remind students to think the one on the bottom is the root, because roots live underground, and so that ends up becoming your root here. The one up here, some people believe in a higher power, so it's higher in the fraction, so it goes as the power there, so there's a higher power. Maybe a way to remember it. So how does this look? So if we have 2 to the 3/4 power, we could rewrite that as the 4th root of 2 to the 3rd power. And in later chapters we'll work about, can we simplify this, when can we simplify this, but right now we're just going to be rewriting that. We can do this with variables. X to the 1/2 is going to be equal to the 2nd root of x. Now often with a 2nd root, you guys are used to taking square roots. We don't need to write that, so we can just write the square root of x. We also want to be able to go backwards. So if you are given something like the 3rd root of x to the 5th power, we want to be able to rewrite that as x to the 5/3. So being able to go back and forth between the two different forms is what we want to be able to do with rational powers in this chapter. So ultimately you'll be asked to apply multiple of these properties together to simplify one specific example. So if we look at the following problem, we've got a lot going on. So we can work in a number of different places. I'm going to start by distributing this 3 to the 2 and to the 5 in the numerator. So the numerator is going to become x to the 6th, y to the 15th. The denominator, I see z to the 0, that's going to be 1. If it's 1 times something else, I'm not going to need to write that because it's just going to be that thing. I see the negative 3 exponent here. It's got to distribute to everything, and don't forget the 2. The 2 needs it as well, so it's 2 to the negative 3rd. X to the negative 2 times negative 3 is x to the positive 6, and y to the negative 12th power. There are multiple ways that you could go about finishing this problem from here. My suggestion would be to get rid of the negatives first. So I'm going to take anything that has a negative exponent, and because basically the rule is to take the reciprocal, they're going to move sides from either numerator to denominator to denominator to numerator. So I found these two, so I'm going to rewrite that up here as now 2 to the positive 3rd, x to the 6th, y to the 15th from before, and now I've got y to the 12th moved up there to join it. Left on the bottom was an x to the 6th power. So now I need to simplify. I see an x to the 6th on the top and an x to the 6th on the bottom. I could subtract those, and I realize that those are going to be completely gone. 2 to the 3rd power is 8, and we have y to the 15th and y to the 12th, so that's going to be a total of y to the 27th power.